Okay, we're going to be looking at how to improve our solutions from where we started off last time. So we're going to use a method called the iterative method. Iterative method. Iterative process. And this is a way of refining our first estimate of the solution to get it closer to the true solution of a function. So when we had this is going to help us find values that are closer and closer to alpha, which is the root we're looking to find. So let's consider a function f of x is equal to x to the power 5 plus x minus 1 equals 0. And we know that that alpha is between 0 and 1. This is a reasonable starting point, but probably it's not accurate enough if we wanted a solution to the equation in the real world. What if we needed to find a value to one significant figure? How can we find that? So we're going to arrange f of x. So we've got f of x equal to 0. And so we're going to rearrange this so that x is going to be some function of f. So if we do that, we end up getting x is equal to x to the 5 minus x to the 5 plus 1, or 1 minus x to the root of 5 to the square root to the power 5. And so that's one possible arrangement that we can do to this. And we're going to use this as a value of x. Now we already know that we have a good starting point of x equal to 0.5. So let's test how accurate that value is. So if we have 1 minus 0.5, that is going to be 0.87055. So we're going to draw a table. So our value of x, we have our value of f of x, which is this. And remember, we want a value to be correct to one significant figure. So our x, the value that we have for x, and the value for f, big F of x, the same to one significant figure. So we had 0.5 and our value for f of x was 0.87055, and they're not the same to one significant figure. Now what we could do is we can graph these two functions. So we've got x. Let's call this y equals x. And here we've got y equals 1 minus x root 5. And this is 1, and here's 0.5. So 0.5 is here. Now what we've done is we have raised this, we're going to, then the value for f of x is up here, which is not very accurate. So now what we're going to do is the value that we got for f of x, we're now going to make that into our value of x. And we're going to slot this in. Now, on your calculator, you've got the answer button. So you've got this little button, I'll put it up here. And you can use that instead of having to chug all the numbers. And you can just write this in, instead of x, you put in answer. So the last answer will be replaced by we put into here. And that will make these calculations a lot easier because you're going to have numbers with to lots of decimal places. So plugging this one into here, you now get what? 0.66438. Still not to one significant figure. But that's come over to about here now. And now we're going to take 0.66438, and that will then give us 0.80383, and that's still a no. Then 0.80383 will give us 0.72197. It's a no. Then that will give us 0.77413. That's still not the same to one significant figure. So you can see what we're doing each time is a bit tedious, but each time we're doing it, we're getting closer and closer to the value. So we're getting this spiral shape if you were to make that bigger. Like that. Oh. And so you're looking for where these two functions hit here, and that's the and as we get to one significant figure the same, we'll get to that point, and it's a close approximation of the actual root of the function. Now where were we on this? So 7741, putting this into the function, we get 0.7474262. But that, although they're both at 0.7, that if you make this to one significant figure, that's going to be 0.8, and this is going to be 0.7, so that's still a no. Then 0.474262 is 0.76227. That's still a no. Now 0.76227 will become 0.75026. Now that rounds up to 0.8. That rounds to 0.8, so that is a yes. So we've found that alpha is 0.8 correct to one significant figure. Now each test that we run is called an iteration. So each test is an iteration. And each time we do it, we're getting closer and closer to the actual result. Now, if I'll quickly add this in here. So in this relationship we had x equal to this function f of x. So what we're doing here is each time x to the n plus 1 is a function of some value f to x of n. So here this is x to the 1, this is x2, this is x3, this is x4, and then you're using these to get to feed your next value of x, and then it all comes down to, so 5, 6, 7, 8, so on and so forth. Let's look at another example, and that will hopefully start to make a bit more sense. So the equation x squared plus x minus 3 equals 0 has a negative root. Alpha. So firstly, show that this equation can be rearranged as x equals 3 over x minus 1, and then use the iterative formula x to the n plus 1 equals 3 over x to the n minus 1, with a starting value of x to the 1 is minus 2.5. To find alpha correct to 2 decimal places, and give each iteration to 4 decimal places where appropriate. So firstly A. So we have x squared plus x minus 3 equals 0. So let's divide through by x. So that's going to give us x plus 1 minus 3 over x equals 0. Now we can rearrange this to give us x equals 3 over x minus 1, which is what they wanted. Now we need, for B we're going to need a nice big table. So our x1 is minus 2.5. And now we've got x n plus 1 equals 3 over x n minus 1. So our x2 is going to be equal to minus 0.2. So are these correct 2 decimal places? No. That's a no. x3 is going to be slotting this into here, so it would be 3 over minus 2.2 minus 1, which is equal to minus 2.3636. So this is 2.3, 2 points, so that's no. x4 is going to be equal to minus 2.2692. These are not equal to 2 decimal places. x5 will be equal to minus 2.3220. Again, they're not the same to 2 decimal places. x6 is going to be minus 2.2920. Oh, to 2 decimal places, so no, that's not. Just doing significant figures there. Minus 2.3089, so no, because that'll be rounded up to 1. x8 would be minus 2.2993. So again, no, but we're getting closer. Minus 2.3047. So this is going to be rounded up to 30. This is rounded to 30, so yes. So alpha is minus 2.30 to 2 decimal places. And you can test your answer. So you could test this by putting this into our initial formula and using the sign test with the two values that we have here. Let's do another one. The equation e to the x minus 1 equals 2x, and it has a root alpha equals 0. So firstly, show by calculation it has another root beta such that beta is between 1 and 2. Secondly, show that this equation can be rearranged as x equals the log of 2x plus 1, and finally use an iteration based on the equation in B with a suitable starting value. And it's correct to 3 significant figures. And give each step to 5 significant figures. Okay, so firstly, so we're testing the root between 1 and 2. So f of x is e to the x minus 1, and we rearrange it to be minus 2. So we're going to find f of 1 is going to be e minus 1 minus 2 which is minus 0.2817. Now we want f of 2, which is going to be e to the 2 minus 1 minus 4. So that is, working that out, we get 2.38905. So change of sign implies a root is present. So next step is to rearrange to get this. So we've got e to the x minus 1 equals 2x. So we'll get e to the x equals 2x plus 1. Now we'll take the log of both sides. Which just gives us x equals the log of 2x plus 1, which is what we're looking for. Now, let's go on to the final part of this. So C. So we've got a suitable iterative formula of xn plus 1 equal to log 2xn plus 1. And let's make our starting value halfway between the two. So x1 is going to be 1.5. So x1 is equal to 1.5. So we're looking for 3 significant figures. So we'll write this down here. So we'll put 1.5 in here, and we'll get our value for x2 is going to be 1.3863. So 3 significant figures. Well, that's obviously not the case. x3 is going to be 1.328278. I'm not going to write down all the calculation for each one because it's a bit tedious. 1.2962, I've not been written, so that's no, no, and 3 significant figures still. Oh, x to the 5, 1.2788, so no. X to the 6, 0.2691, so we are getting there, but that's still no, we're getting closer. X to the 7, 1.2636, so that'd go up to 7, and that's the 6, so still no. X to the 8, 1.2605, so this would be yes. So beta to 3 significant figures would be 1.26, and again you can test that by using the change of sign method by putting in these two values into our original formula and seeing if that is correct. So I hope that helped.